Okay, well, thank you. Thanks for inviting me, and thanks for sticking out for the last talk of today. So the work I'm going to talk about is joint work with Anton and Evsev. 3 of the talks in the abstracts, at least for the conference, were joint work with Anton. Sinead didn't give hers because she was sick, but Sasha Klesjev's also going to talk about him. So it's a great tragedy he's died, but I guess he's here in some way or form. Okay, so I want to start at the beginning. So ultimately I want to try and tell you a way to understand KLR algebras of types A and C that is, I think, useful. In types A, we have Brunt-Klesjev isomorphism theorem, and that allows us to identify this algebra with an ungraded object that we know and love, and a lot of the work that was done, at least initially with these algebras, used that isomorphism in a very crucial, important way. In the other types, these algebras were just completely new. No one had seen them before, or no one recognized them, and bases generally aren't known for the cyclotomic KLRs. For the KLRs upstairs, they have a nice faithful polynomial representation, so they're quite easy to understand, but the cyclotomic quotients are actually quite tricky to play with. And the approach that I'm going to do is going to give us some information about what happens in type C, and give us more information about type A as well. So I'm going to take what Stuart Martin said to heart and start at the beginning. Well, Gordon James, I guess, said it. So I want to use content functions, so let me quickly just review what contents are. I think we probably all know, but I have partitions. I'm going to think of partitions as being diagrams. I want to have standard tableaus where I increase along the rows and down columns. I've got 30 slides here, but I've been told I can go over time because it's the last talk, so that's fine. Is that better? Okay. So I think we all know what standard tableaus are, and probably I'll stop around slide 18, but if I feel energetic, we might go to 30. Later on, I use these tableaus T upper lambda and T lower lambda. Leron introduced them, but he got the notation wrong. T upper lambda is this one, where I read along rows, and T lower lambda is where I go down columns. I'm also really going to use multi-partitions and multi-tableau, but in all my examples, I just use level 1 tableaus because it's easier and easier to understand in some sense. Contents, I think we all know what contents are as well. We just take the difference of the column index and the row index. So there are the contents inside this tableau 4, 3, 3, 2. The content of a tableau, I simply look at the corresponding box where the number is, and that's my content. So I think here I've got my content of M inside T. I just look at where M is. If it's in row R, column C, then I take the difference of the column index and the row index. I want to build contents into these KLR algebras, and I want to try and convince you in some way or form that semi-normal forms and the semi-simple representation theory of Sn lives inside KLR. That's part of my aim. Contents, I guess that they were first played with by Young back in 1901 or so. Korkov and Vershak have this really nice way of showing how they just naturally have to be there in the representation theory of Sn, where they start with this Gelfand-Stettin subalgebra or using Murphy elements. But one of their key properties is that, if you haven't lost the slide, one of their key properties is that contents distinguish between tableaus. So in some sense, almost all the elementary ordinary representation theory of Sn follows from this very simple fact that 2 tableaus are equal precisely when their content sequences are equal. And the proof is simply observing that the contents are constant on diagonals, and so the addable boxes have different contents. And so you argue by induction and you're done. Okay? So that is really, I think, where it's all you need to do to construct representations of Sn. So let me just quickly remind you what they look like, because I want to do a generalization of this. So let me let Sn be S1 up to Sn minus 1, generated by the simple transpositions that satisfy the Cox relations. And then we have Young's semi-normal form that says that we have a unique module which has a basis indexed by tableau, and the action on this module is given by this beautiful formula where I just look at the difference of contents. So I've got the difference of kth content and k plus first content, and then I have this little funny rational number that comes up there. Now, there are many other ways of stating semi-normal forms. One of the most amusing facts I think about the semi-normal form is it tells you how the simple transpositions act, but in some sense, the most important fact of this theorem is that if you look at the Murphy elements, which I forgot to define, it looks like, these just act on these basis vectors as eigenvalues. So Lm is just 1m plus 2m all the way up to m minus 1m. So these things commute. And I like to think of this as being some sort of averaging operator on the numbers 1 up to n. Okay. So from the formula there you can derive this, but in fact it really goes the other way around. If you have a basis of eigenvectors for the Murphy elements, this forces the action of the symmetric group to be given by something like this. And it's a very simple calculation. It's not hard to do at all. In general, you get some constants up here. It will be some beta to k of t's. And it's very easy to check that these betas satisfy some relations. So there is something like a quadratic relation, which really comes from the SI squared equals 1. And then there's two braid relations. It's very easy to check this. What's going on, of course, is that these BTs are eigenvectors. Eigenvectors are unique only up to a non-zero scalar. If I change my eigenvector, I've got to change my representation. And this is how the representation changes. So you conjugate by a matrix, and you get these betas changing in some way. But that's really what a semi-normal form is. It's really coming from these bases of eigenvectors, and then we build that into everything, and we're done. Okay, so I want to build these into KLR. So let me define KLR. We've seen it a few times already, but let me do another time. I want to do it slightly more generally than it's been done so far. Let me just start with an index set, and I want to take K to be a positively graded commutative ring. So if you like, K can be Z, everything's in degree 0. But it could be K of X, where X is in degree 2, or it could be K of X1 and X2 and X3 and X4 and so on. I mean, it's just a positively graded ring. I want to take a Cartan matrix, which is symmetrizable matrix. And then I want to take polynomials, Pij of uv, which sit inside K of uv, with the property that the Pi's are 0, and then I want to let Qij be what I get by taking the product of these two things. And I want to assume the Qij's are this way are monic and homogeneous of degree minus Cij, where Cij is in the Cartan matrix. Okay. One example, if I had a double edge going from I to j in the Deacon diagram, then I could take this polynomial here. The cases I'm interested in are really A infinity, C infinity, affine C1 and affine A. And I'm going to use the usual Lie notation, which I won't say anything more about. I just assume that we've seen it before and know it. But really, from my point of view, the Lie notation is just bookkeeping material. Okay. If I take my symmetric group, it acts upon the set of I tuples. Remember, I was my vertex set for my Cartan matrix or the corresponding quiver. So I act by place permutations. And I want to let I sub alpha, where alpha is a element of the positive root lattice, to just be those I tuples such that if I sum up the corresponding alphas, I get my root. And then the KLR algebra, or quiver Hecker algebra, is the algebra generated by these idempotents, these psi's, and these y's, subject to these listed relations. And my q's appear in two places. They occur here, and they occur here. And I haven't defined that, but in fact, this thing here, this partial q nonsense, is just this difference. Okay, so that's what the relations is. And in some sense, this slide's useless for you if you haven't seen it before, and if you have, it's useless as well because you know it. But just to be perfectly correct, there's the definition. The most important aspect of this is that these algebras are graded where I put these idempotents in degree 0. The y's, well, typically they'll be in degree 2, but it depends upon the Cartan matrix. Okay, so this will be an even integer generally. And the size, when I project them on the idempotents, are also the degrees given by, again, the Cartan pairing. Okay, so these algebras are what I call the affine KLRs, but I probably shouldn't. I'm actually interested in the cyclotomic equation of these, which I'll define in a second. Leron, when he talked about these, and also Louise had E brackets I. I use 1 these days because E for me is the number of elements in the set I. It's useful to think about the relations in terms of diagrams. So I can think about my idempotent as just being a bunch of vertical strings where I've got the residues in I labeling the strands. The Y, I just want to put a dot on the rth string, and the psi I can think is crossing two strings. I want to push this because towards the end I need to generalize this. If I take two such diagrams, I can just put them to the other to multiply. If the residues don't match up, then I get 0. And then the relations I can think about in terms of these diagrams as well, just the certain local operations. So if I want to move a dot past a string, I need to look at the corresponding residues, which I didn't write down, and then if they're equal, I get an error term, and if they're not equal, then it just commutes through. And then I get braid relations by just moving strands across as well. So all the relations I can think of as these local operations on diagrams in this fashion. And then here's my cyclotomic KLR. So the quotient, I want to quotient out by some polynomial. So this ki1 for me is actually a homogeneous polynomial where the degree is given by the number of times alpha, or lambda I appears in this dominant weight. The most common example that we've seen before is simply to take this kappa polynomial to be just u to this index, but I want to allow myself to take more general choices of kappa. Okay? So it's just some homogeneous polynomial with the right degree. Okay, so that's what I want to play with, and I want to try and understand these algebras really in types A and type C. Let me quickly also review cyclotomic heteroalgebras. So we saw this in the last two talks as well. Let's just quickly go through it. I wanted to define it a little bit differently. So we have this algebra which has this nice presentation. This morally is a deformation of the group algebra of a cyclic group of order L reached with Sn. But the presentation I've got slightly different because I've got slightly different relations for the L's and the T's. So this presentation here is the Ricci quirky algebra when psi is not 1, but when psi is equal to 1, it's the degenerate Ricci quirky algebra. And we have this nice basis theorem for this thing, and in particular, this algebra is free of rank L to the n factorial. Okay, so Brundle and Kleshchev showed that these two algebras are in fact isomorphic. Okay, so here I've got a parameter which is a 2e through each of unity, the way I've set it up, and we have certain parameters which depend on lambda, and then we get an isomorphism. A few remarks about this. This theorem only holds over a field. They're both defined over, say, z of zeta, but the theorem's not going to hold over this ring. I can send you the slides. That's fine. So the way Brundle and Kleshchev prove this is they construct isomorphisms in both directions, which I hope that I won't be saying this, but it's an ugly proof, but it's a beautiful result. Rouquier, I guess, has a slightly nicer proof, although there's one part of Rouquier's proof which I at least don't understand. So, but I think that's me. The main consequence, of course, is that we now know these algebras are graded. From the KLR point of view, we also know what these algebras are. We have a nice basis and so on. Well, actually, we don't have a nice basis from this theorem because the basis over here is not going to be homogeneous in general. And also, in the special case of symmetric groups, which corresponds to L equals 1 and lambda being lambda naught, or in fact, any fundamental weight, we get that we have a grading upon the group algebra of the symmetric group. So this is very nice in that we understand these KLR algebras of type A, the cyclotomic KLRs, but in general, we don't really understand what these things look like at all. Okay. So I want to try and convince you seminormal forms are the right thing to do in the KLR world. So what do seminormal forms possibly look like in this setting? If I take a set of tableau, I defined contents before. If I just reduce the contents mod E, where E is any integer bigger than 1, then I can write down a residue sequence in this way. One of the things that Brundle and Kleshchev proved, as sort of a side note in their paper, was that there's very nice representation in the semi-simple case, which are homogeneous and given by something like a seminormal form. So I've got something like a spec module, which has basis indexed by the standard lambda tableau. I put all of my basis elements in degree 0, and then I act by the idempotents. Well, they should just simply look and see that they've got the same residue as the tableau. The y's kill everything, and the psi's just happily commute the tableau in the natural way. And if SR of t is 0, then that basis element is 0. So this is an analog of the semi-normal form. In this special case for a semi-simple KLR isomorphic to the symmetric group, and there's an analogous theorem if I take an arbitrary KLR of type A, and I force myself to semi-simple. So morally, these Y's really look like the UC Murphy elements. In fact, the Y's actually are the nilpotent part of the UC Murphy elements, and in the semi-simple case, the nilpotent part is 0. So it's not surprising that they act as 0. So it looks like in this semi-normal representation, Y should act as 0. But that's not quite right, actually, because as I said, the Y's are the semi-simple part of the UC Murphys. The other part of the UC Murphys is actually hiding the idempotents. So the idempotents are certainly not acting as 0. They just pick out a particular tableau for me. And so you see some part of the UC Murphy element is acting as 0, but some part is not. So somehow in the KLR world, I should split up my UC Murphy elements into semi-simple parts and non-semi-simple parts, but I need to keep track of residues now and contents. So in the semi-simple world, my content functions are all 0, but my residues are playing a role. So unlike in the semi-simple representation theory of symmetric groups, where I just have contents and they tell me everything, in the KLR world, I should have content and residues, and I should use both of them. Okay. The difference. So here I have contents. My contents are 0. These are acting as 0. Yeah, but that's only, well, it's not really UC Murphy at all, because these YRs are 0 in this case. But over here, I've got my UC Murphy elements acting via residues. So the fact how this part of the KLR. So the content, remember, was just the content of M in T was just the difference of the column index and the row index, and the residue of M in T was the content mod E. Okay. So in this picture, the residues are exactly hiding in this residue sequence for the tableau. So the residues are doing something important here, and the contents are throwing away. But I need to have both somehow. So this picture holds more generally. So Kleshef and Ram classified irreducible homogeneous representations of simply laced KLRs, and they have a similar sort of semi-normal form with a diagram combinatorics built on top of the Dinkin diagrams. Okay. So in all these examples that are out there at the moment, everything is semi-simple, and so the Y's are all acting as 0, and that's forced because if all these things are in degree 0, Y's are in degree 2 in this case. So if I act by something of degree 2 or something of degree 0, I get something of degree 2. Oh, nothing of degree 2. So I have to throw that out. So this is forced. Yep. If I allowed my spec module to have degrees that weren't constant, then I could allow my Y's to act in a non-zero way. And what I want to do is describe some semi-normal forms that we can use to describe non-simple blocks. So the starting point for this, in many ways, was that Jun Hu and I proved that if we work over some sort of modular system, you can write down a KLR-like presentation for these Ricci-Koike algebras, where you deform the relations in some way or form. And Anton looked at this and he said, well, why don't we try doing it this way and get some sort of greater deformation? So that's really how Anton and I started working on this. And we'll see a little bit maybe how that comes about. So let me define what content systems are. So very quickly I defined these Q polynomials which determine my KLR algebra, and I've got these polynomials which give me the cyclotomic quotient. So in order to distinguish my KLR, which I know and love and already work with this deformation I'm going to define, let me write R lambda n Qi kappa Ki for the algebra determined by these polynomials. So I wouldn't be able to distinguish it from the other ones that come up. And I can write down a weight in the same way. So notationally, it's convenient to take a quiver, which is just a number of copies, L copies of the A infinity quiver. So A infinity is just the line Z. Okay, so I'm taking L copies of Z, where L is the level of my dominant weight lambda. So explicitly, this has vertex set just given by 1 up to L cross Z, and I just have edges from LA to LA plus 1. That's 1 plus 1 orientation. Then, by coordinate system, what I mean is a pair of maps from the vertices of of this quiver. So R goes from the vertices into set I, which are my residues in some sense, and C goes from the vertices of J into my ring K, my positively graded ring. And they have to satisfy some properties. So the first property says essentially that I can recover my K polynomials from this data. So that the initial residue that I get is going to be the residue coming from this weight. And I can get the polynomial, kappa I of u, by simply substituting in the corresponding values at 1, or at 0. Okay, so I recover my kappa polynomials. The second almost says that I can recover my Q polynomials from this data. So at the moment, I is any type of quiver. Okay. So now, if I look at the Qij polynomial evaluated at the content and V, then it should be equal to this. So I look at B being A plus or minus 1, and I match up the residues of B with J. And if they match up, I get this product. And by this little squiggly equal sign here, what I mean is that these things are equal up to a unit. So next, one of the most important properties, I think, of content functions is that contents distinguish tableaus. I haven't got tableaus yet, but what I want is that if I take distinct vertices in my quiver gamma L, then they should be distinguished by these two functions. So my residue functions and content functions combined can distinguish between the vertices of gamma L. And then finally, there's another technical condition that I don't want to state. It's not that complicated, but I think it's easier to leave it out. So this is what a content system is. And what I want to do is use this to do things. So first, do these things exist? Well, the most simple example is to simply take I to be JL, so just take the quiver gamma, and then I can write down a content system where this R is going to be the identity function, and my contents are all 0. So it's easy to just check, and you go through, and maybe this shouldn't be surprising because in the example I gave from Rundin and Kleshchev, essentially they wrote down a semi-normal form where my contents were all 0. Yes? And this really corresponds exactly to that case. If I take the quiver, cyclic quiver with E plus 1 vertices, then here's a nice content system. We simply can take the content. So I guess I should have a Z up here. I've sneakily snuck into level 1 here. So if I think about level 1, I've got my vertices going along here, 0, well, it starts at minus 1, I guess. It just goes on. At some point I'll get to E, then E plus 1, and so on. So my residues, in some sense, really should just merely go along and do this. And then the question is, what do my contents do? So the residues are sort of forced because if I've got to start at a prescribed place according to the first condition in my content function. With contents, I haven't told you what my Q polynomials are, but if I have an edge from I to I plus 1, the corresponding Q polynomial I could take to be this, for example, where this x is just an indeterminate. And I haven't really incorporated a grading, but if I incorporated a grading, I'd say that the degree of x is 2. Yes, that's fine. And the conditions that I've got on my polynomials say that, so since I've got a level 1, let me just write A here. This should be a product over B of V minus the content of B, where the residue of B is J. And so if at some point, so I've got K mod here, if my content was K of X, then what happens at K plus 1? So I get K plus 1 mod E here, that's actually forced. What can I put here? Well, on the one hand, I'm going to have So when I substitute this in here, I'll get kx, and then I get v. And over here, I've got to have b minus cb. Yep, that's what my condition gave me. But this has got to also be given by this. So if I plug into this polynomial here I get v minus, well, my u is kx, and I get a minus x here. So putting this together, we see that the content of b is k plus 1x, which is what I've written up there. So really, the content functions are almost uniquely determined once I say what happens at 0. Okay? But they're forced. Now, of course, this content function here is very natural. I've got really just the normal contents. Well, in fact, I'm just mapping k down to k. So I'm really mapping my contents to contents. Because if I think about tableaus, what do my contents look like in a tableau? Along the first row, I do this. And then on the next row, well, secretly, I guess I've really got a minus 1 here. I shift everything across. So if I know the contents in the first row, I know the contents in the second row just by shifting. So this data here would tell me how to put contents into tableaus. Okay, so Rune asked if this is only type A. It's not. If I take type C, it turns out this is a content function. And again, it's very natural. So the residues are merely going along from 0 up to E. Then they fall down from E to 0. And then they go up again from 1 up to E and so on. So they just go up and down, up and down, up and down. The contents, well, they should happily increase. So x, 2x, 3x, up to E minus 1x. This one here corresponds to my double edge in the Dinkin diagram. So I've got an x squared here. So the degree 4 Murphy element is going to act by a polynomial of degree 4. And then I go down, and then to distinguish between my contents, remember my contents and residues together should uniquely determine where I am. So here, I couldn't put e plus 1x, but by changing the sign here, somehow everything works out fine. And again, just by plugging into the Q polynomials, you see this is sort of forced on you. Either I haven't told you what the Q polynomials are. Oh, this is a typo. There should be 2e squared here, 2ex squared. Okay. So generically, these content systems are defined over, say, zx up to, so I've got 1x, and then for each level, I've got another indeterminate I can add. The examples I've given here are all defined over just k of x, where x is some indeterminate, and which I put in degree 2, typically. And then, because we're working over kx, I can simply put x equal to 0, and I'll go from this KLR algebra down to a normal KLR algebra. So this will define for me a graded deformation of the KLR algebra that I really care about. And the game is simply, okay, I want to understand this algebra. This is just a normal KLR algebra, given by the normal relations we've seen. But instead, I want to go away and play with this thing, which is some sort of graded deformation of it. And I want to try and understand what it looks like and use it to understand the algebra downstairs. So we're lifting up to give ourselves a more natural world to play in. So the content functions live in the deformation. They don't really live down here. So one other point worth making is that these content systems are not unique in that, so it depends how I phrase it. If I think about what algebra I'm looking at here, well, the content systems are actually close to being unique. You can change orientations and so on and change them a little bit. But if I think in terms of the algebra I actually really care about, there's many choices here. And this really corresponds to choosing different lattices, I think, in say, a modular system. That's morally what these different choices of content systems are doing for us. Okay, so what can I do with this? So let's fix the content system. I need some notation, I guess. So if I've got a lambda tableau where lambda is now a multi-partition, then I can look at M. M will appear in, say, row A, column B, and component K of my tableau. And I can simply define the content of M in T to simply be what I get by evaluating my content function at K, B minus A. And simply the residue, I can evaluate my residue function at K, B minus A. So B minus A was my normal content. And now I just plug it in as part of my data into these content and residue functions. And then once I have this, I can write down content functions and content sequences and residue sequences for my tableau. And it's very easy to check essentially from this uniqueness condition that I had, condition 3 in my definition of content systems, two tableaus are equal precisely when they have the same content sequence and the same residue sequence. Okay, so I need both the contents and the residues to differentiate between my tableau. So in the examples I gave on the last slide, in fact, the contents alone will distinguish, but in general, we need contents and residues. And then we get a semi-normal form. So let me take the filter fractions of K, just take a multi-partition, and then we can write down a irreducible graded module for this deformed KLR beast, which I'm going to call a blackboard bold S, which has basis indexed by standard tableaus, and the actions given by something fairly close to what Run-Nikleshev did, but it's a little bit different. So my idempotents are acting by residues. So they only care about residues. They pick out the tableau of the right residue. The Y's, they don't act as zero anymore. They're acting by a non-zero scalar. Well, this scalar can be zero sometimes, of course, but in general, these scalars will be non-zero. So I've got an honest action of the Y's now. And the size, well, they act by something which looks very much like the semi-normal action. You know, I've got essentially the difference of contents here, and then I've got some scalars here, and the scalars satisfy the same sort of relations that you get for symmetric groups. They satisfy a quadratic relation, and they satisfy braid relations. You can write them down. It's not hard to do. So it turns out in the ungraded setting, you've got lots of choices for these betas. But in the graded setting, if you want to actually have a homogeneous basis, there's a particular choice that's forced on you, which is quite nice. I won't say what it is, but there's a natural choice in the graded setting for these betas. No. So I guess x is degree 2, but these content functions can sometimes have x squareds in them and so on, because the degree of the y's changes depending. So in type C, y will sometimes have degree 4. Yeah. But in that case, we're acting by an x squared, and so the degrees still match up. Okay. So this theorem is no harder to prove than Young's semi-normal form for symmetric groups. I mean, once you've stated it, you simply merely run through the relations, you check they hold, and you're happy. So that tells you you've got a representation. To check that it's irreducible, you're essentially arguing the same way as for symmetric groups. So there's nothing new here, except the definition of this content system. Once you've got this machinery in place, you throw your old, well-known, much-loved, slightly worn-out tools at the problem, and you see this theorem holds. Okay, so notice that. Let me just emphasize again, these UC Murphy elements, they're somehow embodied in the idempotents and the Y's, and they're both doing different things. I've got some of these things are just acting as projections onto particular eigenspaces, and these ones here are acting as eigenvalues. Let me just compare what happens with the symmetric group and the semi-normal form, just in these two cases, just to ram the point through. So symmetric groups, we have this presentation up here. So we have just scalars, and the scalars have some nice form. If we write down the corresponding presentation from the last slide, in this case, then all I do is I put x's in places. So I put an x here. I should have an x on bottom and x on top, but of course x on x is 1, so I've taken it out. And that's fine, because if I look at the degrees here, this one's going down in degree by 2, and this one is the degree of psi k times y bt. My idempotent is acting as idempotents, and my y is acting as content. And it's just x times the normal content. So this I think is it's really pretty. I just simply put an x everywhere into my normal semi-normal form, and it works for this deformed KLR. Yes?
You said the features were, you didn't have any choice, but you do have a lot of choices in Young's semi-normal form, right? So it looks like...
So if you want to construct a homogeneous presentation, then the degrees are fixed in some way or form. So in this case here, yeah, maybe I should retract from that actually. Maybe the betas are arbitrary still. Yeah. Yeah, because I'm certainly here it works, and I've taken a slightly non-standard choice. Yeah, no, I think I was wrong. The betas you can still choose with a fair amount of flexibility. But at the moment, I actually haven't used the grading. We don't have to impose the grading to get any of this. It just works. Okay. So I said these content systems are not unique, but it turns out they're not so important in some way or form. If I take a KLR algebra with one of these content systems, then it turns out that the corresponding KLR algebra is a split semi-simple graded KLR algebra that is canonically isomorphic to the cyclotomic quiver algebra with this quiver that I started with. And the representations are exactly the ones that I wrote down. And so this is just a matrix algebra in exactly the same way that Young's semi-normal form gives you, say, a Weatherburn basis for the group algebra of the symmetric group of the rationals. This theorem here does the same thing. Okay, so, and the proof, well, the proof really is, did I write down? Yeah. There were some idempotents floating around, and you can decompose these idempotents in the KLR algebra that you started with as a sum of terms here, and these FTs naturally live inside the KLR algebra of this quiver, and then you just have to match them up. So it takes a little bit of effort to do it properly, and hidden behind the scenes somewhere is some sort of complete reducibility theorem in that if you take any module for this algebra, then it breaks up into a direct sum of generalized, to a direct sum of eigenspaces for the y's. So that's a crucial part of the proof somewhere, but that's really where this decomposition comes from. But it's not so hard to prove this, and so this shows that in some sense the choice of content functions don't matter because the formed algebra that you get is always the same, provided you're working over the field of fractions of this little k. Okay. So semi-normal forms are great if you want to study semi-simple representations, but they're not very useful in general because if you look at the coefficients in a semi-normal form, you can't reduce them mod p. So in order to reduce mod p, we have to choose a nice basis, and well, Leron showed us how to do that in his talk. What we can do is simply take the corresponding basis elements in our semi-normal form, corresponding to our initial tableau and our final tableau, and we can hit it with the generators in a nice defined way, and this will generate a lattice for us. So let me try and explain the notation a bit. So I've got my set of multi-partitions. It's ordered by dominance, where if I think of my multi-partitions, I've got an L tuple of partitions, and my dominance ordering just moves boxes up in a diagram or to the left. Okay? So it's natural, I think, to associate this T upper lambda to the normal dominance ordering where I'm moving boxes up and to the left. But I've also got the opposite poset. With the opposite poset, somehow this lower T lambda is the important one. So I want to use a poset explicitly in my notation. So these little triangles are my dominance ordering. So this D triangle to the left T and this triangle to the right T correspond to the opposite partial order, opposite dominance order. This corresponds to dominance order. And I just simply define these permutations which map my initial tableau to T or my final tableau to T, and this is sort of looking from the bottom up in the order, and this is looking from the order down. So that's why I've got these triangles there. And then if I simply define my basis elements by hitting it with corresponding size, then I can generate a bunch of elements, and it's not hard to check these things are actually linearly dependent. So here we should be a bit careful because, as Leroy mentioned when he said this at one point, the size don't satisfy the braid relations. So what I should do is I should fix a reduced expression for this permutation, and I should write down the corresponding product of size, and I should hit that against the generator. So the element you get would depend upon the reduced expression, but for any fixed choices that you make, these elements will give you a basis. So I simply just plug together these things, and they give me honest modules, which are now modules for the KLR algebra defined over little k. Okay. I won't exactly go through how this works, but so in my world, this is a spec module and this is a dual spec module. In the classical symmetric group world, I guess this is the spec module, that's a dual module. But they're honestly dual modules that you get this way. And they're very naturally associated to these partial orders. So doing this, we recover the graded spec modules of Brunder, Kleshchev, and Wang, and the dual graded spec modules of Hugh and myself. In type C infinity, we'll get the graded spec modules of Ariki, Park, and Speyer. If we go to affine type C, these are the spec modules that a Ricci-Parkin-Speyer conjectured should work. Okay, so, and of course, when I say that this recovers it, what I really mean is we take these spec modules which are defined over, say, Zx, and now we specialize x to 0. That will give us modules now defined over Z, and we're happy. Okay. So these modules come equipped with non-degenerate symmetric bilinear forms, which are homogeneous to degree 0. So if I take the localization of Zx at the prime ideal x, I have a PID, and I can look at the answer filtration, but look at all those things inside the module such that the inner product, say, M and A, will live inside x to the k times A. This is a nice filtration. We can define corresponding filtration downstairs at x equals 0 simply by setting jk of m to be essentially just reducing x mod zeros. But I have to do it like this. I have to add on x times mx and multiply by mx. So this gives the filtration of the module for my KLR algebra downstairs. By construction, this is quite nice. This quotient of jk mod jk plus 1 has a non-degenerate homogeneous bilinear form of degree minus 2k. And the aim is to find some sort of Janssen filtration which explicitly describes the sum of the pieces in the Janssen filtration. So I've got to I guess I could just describe this sum, but it's easy to work inside the Grothendieck group. So in particular, via this general construction, we get graded Janssen filtrations for the spec modules and the dual spec modules. So Janssen filtrations have been around for a long time, but these are now honest graded filtrations. So I have a Janssen sum formula for these modules. I'm not going to show it to you. But the formula I have is still wrong in some sense, because the formula I have is for this sum where you forget the grading. So I haven't managed to incorporate the grading into the picture yet. But I'm optimistic that I can do this. But there is a graded Janssen, there is a Janssen sum formula. And so in type A, this is well known in some sense. In type C, it's a new object and should be quite useful, I would hope. One point worth making is it's not clear a priori that this Janssen filtration coincides with the Janssen filtration that exists in the literature already, because the construction here is quite different, and I don't see any obvious way to compare the two filtrations. But it's not impossible, they're different filtrations. So one thing which I have thought I've proved several times, but I keep on finding gaps, is that if I take the quotient of the kth piece plus the k plus first piece for the spec modules in these filtrations, what I should get, I forgot to define them. If I take the graded decomposition numbers, so this is just the multiplicity, so this is downstairs, of a simple module and a spec module, which I think we've seen defined already. So we just look at the multiplicity of shifts of my simples inside my specs, and I take that to the coefficient of q to the k. And what I've done in this slide here is I've written this as a sum of terms d lambda mu k times q to the k. So if I'm working characteristic 0, which actually this slide says, then we know these things are actually, so they're always, by definition, Laurent polynomials with non-negative coefficients, because the coefficients are just multiplicities. But if we're in characteristic 0, then, in fact, they're Cousin-Lucid polynomials, or parabolic Cousin-Lucid polynomials. And the constant term is 1 precisely when lambda mu are equal, and otherwise it has 0 constant term. And in this case, I'm using the positivity and using this bilinear form on the quotients. I'm convinced that these successive quotients are just the sums of those module shifts. Oh, that's actually wrong. It should be shifted in degree k. So the statement there should be that jk mod jk plus 1 is a direct sum of the mu d lambda mu d mu shifted by k. So that's what I think is true. So for level 1, I can prove this is true using results of Shan, and they're very strong results. And for higher levels, I'm sure it is true, but I can't see how to prove it. If this was true, then I can now prove that, in fact, the answer filtrations, the radical filtrations, the Sockle filtration, and the gradient filtrations of these modules coincide. So technically, I can't really define a gradient filtration, but because of this result that these polynomials, or these gradient filtrations are always polynomials, the basic algebra is a positively graded algebra. And so if you take a module for the basic algebra, then you can simply just define a filtration where the kth piece is all those things of degree k or larger. And so since there's a Maurice equivalence, or gradient Maurice equivalence from the algebra to the basic algebra back again, you can take a module, you can push it through the Maurice equivalence to the basic algebra, define its gradient representation there, and pull it back. But morally, the kth part of the gradient filtration is just the sum of all those d mu shifted by degree k, or larger. So, yeah. So this came as a slight surprise. I've been wondering for quite a long time whether this could be true. So typically the way one tries to match up things like gradient filtrations and radical filtrations is using, well, first showing that your algebra is Cazul, and then once you have a Cazul algebra, you have this very, very simple proposition in BGS that says that if you have a module with simple head, the radical filtration of that module coincides with the gradient filtration. And the proof is almost entirely elementary, and it relies on the fact that Cazul algebras are quadratic. Sadly, Hecker algebras are not quadratic. So there's no way they can be Cazul. And so you can't use this. But sometime I realized that I can write down these filtrations both for spec modules and dual spec modules. And if you combine these two things, you can take the answer filtrations for the spec module. If that coincides with the gradient filtration, then you can take the dual, and you'll get now an ascending filtration, which has the same multiplicities, because you can check the multiplicities if you have this conjecture, and you can actually check that the radical and Sockle filtrations coincide. Sorry? Yes. Yeah, so the modules are rigid. But this, of course, is only characteristic 0. Okay, so I've gotten sidetracked a little. So what I've done so far is I've tried to convince you that we can write down spec modules for algebras of type A and type C with very little work. And also, for free, it's actually very easy to compute in these things, because you have this semi-normal basis where you're just acting in a very easy defined way. And the transition matrix from the semi-normal basis to this basis, the WTs I wrote down, is also very easy to compute. It's triangular. So you can throw this at a computer, and it will happily compute inside these modules for you. And it's amazingly fast and efficient and does wonderful things. Of course, what you'd really like is not to be able to work just inside the spec modules, but you want to really work inside the entire algebra. And what I want to try and convince you of is that we can do this. So this is really the same as what I said before. I said already this algebra over the field of fractions k, I guess I left off the capital K, was a semi-simple algebra. And it has a basis of matrix units, and so it's graded cellular. Just like we defined, well, in a similar way to how we define the W basis for the spec modules, if I look at the construction of the psi basis for the KLR algebras of type A that Hugh and I did, it's very easy to write down elements psi st for the dominance order and for the reverse dominance order. So you can write them down in almost exactly the same way. These things live inside the integral form, so it's not hard to see at all. If you look at the action of these things on the spec module, of course they act integrally. Everything's fine. The problem is that what you'd really like to say is that these things here form a k basis for your algebra over k. And when you look at the structure constants for these things, again, the structure constants should live over k. If I'm looking just on a spec module, the structure constants are in k, but if I look at what happens on higher up in the cell filtrations, or lower down, I guess, in the opposite order, it's not clear a priori that the structure constants live inside k. But nonetheless, it's true that if we take these bases, then we get two cellular bases for the algebras. So this gives us a greater cellular basis for algebras of, well, these are still over K, so these are still deformed, but we now have K forms. And because this is over little k now, we can set x equal to 0, and we can get that these algebras downstairs are greater cellular. So in type A, this just recovers the basis that Hugh and I gave already. But in type C, this is honestly a new basis. The proof, and the reason why I've left it to last, the proof is reasonably tricky. And one of the really annoying things about KLR algebras is that before I met KLR algebras, whenever I was given a presentation, it was always really, really easy to write down a spanning set. Proving linear independence from relations was tricky, but a spanning set was always fairly straightforward. The KLRs, sadly, both things are hard. So this semi-simple deformation solves linear independence. That's fine. It's very easy to check that these psi STs, the up and down partial orders, are independent. That's not a problem. What's tricky, though, is showing that they span the algebra. And this was something that I bashed my head against for a long, long time. And then back in, was it April, July, Chris put a paper on the archive that gave a different way of constructing bases for KLR algebras. And I resisted it to start with, but after some time I've given in. And I want to quickly describe how we can use these Webster algebras to define KLRs, to check the spanning. And as a consequence of this, we also get other benefits in that just as Chris constructed many different bases depending on the loading, you get different cellular bases depending on loading in this setting as well. Sadly, the deformation makes it no easier. So the argument is roughly the same as what Chris did. And there are some differences, but it's a similar sort of proof at the end of the day. As Riki's already said, there are some people in the East who don't like Webster or have difficulties with Webster's papers. There are people in the West as well. I think it's universal. And his ideas, though, I think are brilliant. The details in his papers are terse. But I think it's, yeah, I think what he's written down is, this presentation is really quite amazing. But because of the skepticism, I'm taking special care to write this out very, very carefully, which probably means it'll take me a while. So let me quickly, in 5 or so minutes, try and give you a flavor for what's going on here. So I've got a dominant weight at level L. We want to throw in a loading. So this is just a sequence of integers. And I want my loading to be increasing, because that makes it easier, and I also want them to be distinct mod L. So somehow the level's playing a big role here already. Okay. And I'm going to do things a bit differently to Chris and Ben, in that they work with 1 on epsilon, well, epsilon some tiny number. I don't like tiny numbers. As far as I'm concerned, all numbers are integers. So I'm going to force that to be true. I want to extend my loading to the set of triples. So L is my component, R is my row index, C is my column index. And I wanted to just define the loading of this triple to be n times theta L, capital L times C minus R plus R plus C minus 1, where n's at least as big as 2n minus 1 and L's at least as big as 2n minus L. So essentially all I've done is I've taken Chris's equations and I've multiplied through by 1 on epsilon to clear out the epsilons everywhere. So it's just simply rescaling. These conditions here, it's very easy to check. They're there precisely to make sure that this theta is injective on different nodes that can appear in my tableaus. Okay. If I take a partition, I want to define the loading of my partition to simply be the loading of the nodes in the diagram for that partition. Okay, so I get a bunch of numbers attached to my partition this way. We can define a dominance ordering by simply saying that lambda is bigger than mu in this dominance ordering if we add up the number of the loadings that are bigger than some fixed theta of LSD, the loadings in lambda there should be at least as many as the loadings in mu. So this is pretty much exactly what we do for the normal dominance ordering. For the normal dominance ordering, I could take theta equal to the identity map. Okay, that wouldn't quite fit with what I said here, and I could just take the lexicographic order, and this would be exactly the dominance ordering. So if I ignored my thetas and took just the lexicographic ordering, this would recover the normal dominance ordering of partitions. Okay. Then there were these funky Webster tableaus, and they're a little bit funny. So I got a tableau of type mu. So it should be a bijection from my diagram for lambda into the loading for mu, and then it should satisfy these conditions. So if I've got a non-empty component, then the entry in the first box should be less than n times theta k. And then as I read along rows, I've got this condition, I've got to be less than plus L, and when I go to the columns is minus L. So there's some funny conditions here. And I just want to let SS standard be theta lambda mu be the set of Webster lambda tableau type mu, and I'll add them up in various ways. And if I take omega to be this smallest partition, then let standard theta of lambda be just the semi-standard Webster tableau of type omega n. So there's a typing here. So we should think about these tableaus as being semi-standard tableaus rather than tableaus. And if I take the semi-standards of type omega, in the normal world, that will give me my normal standard tableaus, and in the Webster world, it does too. Okay. So this is just renotation. So I mentioned already that I can think about my KLRs in terms of diagrams, and I take diagrams like this, and I write my relations like that. I want to do the same sort of thing for Webster diagrams, except now life is more complicated. So up here, I've only got one type of string. For Webster diagrams, I want to have red strings, solid strings, and ghost strings. These should be called solid, shadow strings, I think, but they're called ghosts. And the ghost strings should be L units to the left of the corresponding solid string. Okay? So they're really shadowing their solid. And they have residues in the same way that KLR ones do. And I want to define them up to isotopy. And I want to allow solid strings to have dots. And I want to disallow the following types of crossings. So this is fairly standard. I don't want to have a tangential crossing. I don't want to have fat crossings. I don't want to have, I guess fat's probably un-PC these days, but no. No fat crossings. Triple crossings aren't allowed, and I can't have dots on crossings either. Okay? So fairly standard. If I look at where this comes from, it really comes to this sort of picture. So here is an example of loading. So here are the loadings inside the tableau 421, and I've tilted my tableau in the so-called Russian convention so that it goes like this. So I want to think about my loadings being x coordinates, and I want to drop from the x coordinates down to my little tableau here. So if I look at this, I've got 1, which is going to go over here, because this is on 0, the red line's on 0, and I've got this 3, which will go down to here. So over here, I've written down the numbers on the bottom of the string. So the important point somehow is that things on the same diagonal are close together, and as I move along my axes, I get further apart. And then I've got the ghost strings, which is shadowing. So the ghost for this string here is this one, this ghost is here, and so on. So somehow the ghosts cluster around other strings, and they stop things moving in some way or form. And here's another example. Here's the level 2 example. And I've chosen, I haven't written down the loadings in this case, but this is written to scale. So things are very close together, and that's somehow forced. In Chris's world, things are epsilon apart. In my world, they're 1 apart, but it's just a scale factor. So I've got integers, Chris has 1 on epsilons, but the pictures are exactly the same, and they're a bugger to draw. And if you get them wrong, if you happen to draw these ghosts in the wrong place, then the picture's wrong. So these are really painful to work with, but that's what they look like. If I change my loading, so here it's 0, 1, here it's 0, 5, things get spaced out. But things will stay together in the same sort of way. So these 2 strings here are on the same diagonal. They're still on the same diagonal, but my scale is now squash things in. In general, what happens is that if I look at it on a given diagonal, they'll be clustered. So the 0th diagonal, the one directly on the bottom of the tableau, they'll be clustered next to the red strings, and then I'll get the next diagonal out here, the next diagonal here, and the picture just goes out like this. So strings cluster according to diagonals. That's the moral. We can compose these diagrams in the normal way. So let's just do a quick example. So they don't have to be vertical in general. They can do random things. So here I've taken this diagram, I've reflected it to get another one, and then I just put them on top of each other. The way I set things up, these red strings never move. They're always fixed. But the solid strings can move in isotopy. But that's just a detail we don't need to know. And then we define our Webster algebra just to be the K algebra spanned by the isotopy classes of diagrams. And the multiplication is given by composition. And we have lots of what I call bilocal relations. So they look a little bit like this. I'm not going to dwell on them too much because this is slightly painful. So they're bilocal in the sense that here I've written 2 diagrams, or I've written 2 parts of diagrams. But attached to this crossing here, there's a ghost somewhere. Okay? So there's a ghost off to the left. L units to the left will have a ghost crossing. whenever I do surgery on my little diagrams or apply these relations, I've got to make sure the ghosts behave as well and don't do anything strange. So if, when I tried to do these isotopies, the ghost misbehaved, I can't do that. Although in practice, up to isotopy, you can always rearrange things so that everything's clear of itself and it's fine. But with all these relations, I really have to always look at the solid strings locally, and then also at the ghost strings. And I've got to make sure that in both patches, things are well behaved. Which, when you write down examples and arguments, is a real pain, but that's what one has to do. So most of the time, with all these relations, you can move dots through crossings, except when they have the same residues. You can pull apart strings that overlap like this. There's two exceptions when these things have the same residue, and when I'm putting a red strings through, these polynomials come up. So here's my content function. It's inside these relations. Then there's more complicated relations. These are something like grade relations. And these p polynomials that I had at the start, remember qij was defined to be a product of pij and pji. The p's appear inside these relations here. Okay, so there's not that many relations. If you write them all out, it's actually a real pain because I've said with all these relations, the relations commute except for this case. When I write down a full list of these things, it takes me pages. And the reason for this is you have 3 types of strings, and so there should be at least 6 times as many relations, and there are. So if you want to try and look at modules for these algebras, it's really painful, because if you want to check the generators and relations, well, you've got generator relations. The generators are the set of all these Webster diagrams. And you've got relations, there's pages of them, and you have to go through and check them. So it's not going to work. Unless, of course, your module is something like pick a diagram and act on it. And then you're probably okay. But any other sort of module is going to be a pain to check relations. I think it's just not possible. So once one has this set up, for each one of these semi-standard Webster tableaus, you can define a diagram, which just goes from the loading up top to the loading down bottom in a sort of minimal sort of way. And then once you have this, you can reflect the diagram in the x-axis, and you can get a CST which factorizes it like this. Okay. And once you have that, you can check, following the argument of Chris and Webster, that the algebra is spanned by these diagrams. And the proof, in some sense, is quite easy. The proof is simply you pull strings to the left. In practice, of course, you have to do a bit more than that, but that's morally what you do. You pull strings to the left, and eventually they either die or they become standard, and you're happy. And the connection to KLR is that if you look at this idempotent, remember they gave me the standard Webster tableaus, it picks out the KLR algebra that we started with. And let me just finish by giving you the proof. The proof essentially is this. You simply just check that you map the idempotents to the idempotents where all the strings are to the right of the red strings. The y's go to the right of the red strings as well, with a dot on them, and the si's do as well. Now, Chris might object to this point because in his world, you can't drag these dotted lines past the red strings always, but in my world, you can. So checking the relations is actually a slight understatement, because these diagrams a priori don't generate this ideal over here. And there are other more complicated things that can happen, but it turns out they all have a normal form, and this normal form is generated by these things, and so you're actually okay in the end. But it's slightly tedious. And I think, I don't know why I'm saying 30 there, because I think that's my last slide. But at the end of the day, since I've got a spanning set for the Webster algebra, this gives me now a spanning set for my KLR algebra, and then I'm almost done. So it turns out that this basis you get from the Webster algebra doesn't match up precisely with the basis I have, but it matches up modulo higher terms. And so this tells me that my psi bases actually span my algebra, and then I'm done. Although that's actually also not quite correct. This works only for the normal dominance ordering on my tableau when I choose the right loading. But for the other partial order, I can use inner products to then show that gives a basis. So at the end of the day, we get both these bases. And also for some of the theta bases we get this way, you can define dual spec modules in this sub as well quite nicely. So it works out quite well. Okay, so I will stop.
Any questions?
Sorry? There is no slide 30, and I don't know why it's saying 30, because if I try and click through, nothing goes. There's nothing there. So the content system does. So you have to choose the right queues in some sense. So if you pick, say the normal queues using KLR, you can't write down content systems, so they don't exist. But if you choose appropriate deformations of them, then you can. And in some sense, the deformation you choose, the choice of the queues, determines these content functions. Because in the example I showed, once you've fixed a particular value of the content somewhere, that then forces the other values. So the content functions, I think there's probably always two choices. But you have to be clever in some sense in choosing the right choice of queues, or the right deformation of those. Because if you choose the wrong ones, then you get nothing from this. So there are definitely choices involved. But in terms of what we care about downstairs, it doesn't really matter what we do. All we want is one choice that works. Although it does turn out that there are some choices that are better than others.
For every type, you can always make a good choice.
Yes.
Okay, another question?
On page 58, as a result of a format the vertex implies algebra, Seminormal.
So in type A it does, and that's essentially what Chris does. In my case, I haven't actually checked. I think that it doesn't. Because, so Webster makes this remark that if your quiver contains no cycles, then the algebra you get this way is an original equivalent to the algebra you started with, the original KLR. If this basis was cellular, that would actually imply that in type C, this Webster algebra was quasi-hereditary. And I think it can't be, because, well by Webster's remark, it can't be. Although it is possible that if I choose the right queues, it will become so. But at the moment, I've only looked at, well, I haven't checked out to see whether the particular choice of queues will matter. But certainly, I think that in general, in type C, this is not going to be a cellular basis. They won't be linearly independent.
Okay, one more question.
So I'm all for these algorithms, but I didn't understand your point of what you needed this for. So you said just from your deformations, you get linear independence already.
Mm-hmm.
And so why doesn't the result you need follow just from a dimension at that point?
It's not clear they span. It's not clear these things span, and it's not clear the structure constants live inside K. In fact, when I was first doing calculations with these, I made a small sign error, and I couldn't write the idempotence as, say, ZX linear combinations of my basis elements. So it's actually quite subtle. If you make small errors, then the small perturbations on the definitions, then the result is false. It isn't actually a K basis. And there's no reason why it should be.
Okay, let's thank all this afternoon's speakers.